So section 12.7, we're going to talk about how to solve exponential and logarithmic equations. We've done all the legwork, we know all the properties of logarithms, we know really all the properties of exponentials. We're going to tie all this together. The one thing you need to know is what I've been talking about for the last 3 sections. Logarithmic and exponential functions are inverses. What that means to you. In order to solve exponentials, you need logarithms. In order to solve logarithms, you need exponentials. Are you with me on that? Now, the only time that does not apply is on these first 2 examples, which we've already done in this class. These should look really familiar to you, and you should be pretty rock solid on solving those ones. If you think about these, the idea was you're going to try to get common bases. You remember getting common bases? And you say, oh, right, well, I know that if this is 3 to the x and this is 9, I should write this as 3 to the x and 3 squared. Because that's still equal to 9. Are you with me on that, folks? And then how much is x?
2.
Yeah, we understood that if our bases are the same, our exponents are equal, and we can solve exponentials like that if we can find common bases. Raise your hand if you feel okay with that. Yeah, that's really old stuff, right? But that's going to be on your test, so you need to know that. The first thing you look for is, can you find common bases? Also over here, could you find common bases here? What's your base going to be for those?
5.
Sure, you would write 5 squared to the x, 5 to the third to the x minus 2. Is this coming back to you? This was a few sections ago, a couple sections ago. Of course, when you have exponents raised to exponents, you would get 5 to the 2 times x, and you get 5 to the 3 times x minus 2. Notice how the x minus 2 is in parentheses because you're going to have to distribute that. Still so far so good? You better wake it up today. We're going to move today, if you couldn't tell. Had lots of coffee. Great. No, I didn't. Your bases are the same. Of course, you can set your exponents equal to each other. Distribute. And solve. Now, of course, I went really quickly through that because we've done all of that before. Would you nod your head or raise your hand if you're okay with doing these 2 examples? Raise your hand if you are. Yeah, how about this row over here? You guys all right with that? So we're finding our common bases. We're setting our exponents equal. Sometimes they're very easy. Sometimes you have to do some work, but still it's not that big of a deal as long as you can find those common bases. We know that's 5 squared, that's 5 to the third. We multiply those exponents. So 3 times x minus 2, we distribute, and we solve. This should be a piece of cake from here on down, right? Subtract a smaller variable, get the x by itself. Here's the question. You're sure you're okay with this, right?
Yep.
You're sure you're okay with this one? Because you can find that 5. Okay. How about this one? Is that example different than the first 2 examples?
Yeah.
What makes it different?
Common bases.
Here it was pretty easy to find a common base, right? That's 3, that's a power of 3. Here it's easy to find a common base. That's a power of 5, that's a power of 5. Here, can you find a common base? So here's your idea for exponentials. The first thing you try to do in any case, if you have an exponential, which all 3 of these are exponentials, you'll look to see if you can find a common base. Why? Because it's pretty easy if you can find a common base. Common base, no problem. Common base, no problem. Common base. Can you find a common base there?
Nope.
The question is, can you write either of these as the same number to a power? That's a no. No. Through this is 3. They're both prime numbers. There's not even any factors besides 1 that go into that, besides themselves. So there's no way to write these 2 things as a common base. Do you agree that there's no way to write those as a common base? So what are you going to do? Well, I just told you this about 2 minutes ago. In order to solve exponentials, besides the ones you can get a common base on, in order to solve exponentials, you need logarithms. Are you ready to see how logarithms will help us here? This is going to be kind of cool. You're going to be very excited. You should be very excited about this. You should be. I hope you are. Here's the deal. Do you know how you can add something to both sides of an equation and subtract something to both sides of an equation and multiply and divide and take it to a power and do all that fun stuff to it? You remember all that stuff?
Yes.
Is that an equation?
Yeah.
You can do pretty much anything you want to an equation as long as you do it to both sides. We can even take a logarithm of both sides of an equation. What logarithm did I choose? What base is that?
10.
Good, that's a common log. Why am I not choosing log base 3? I could choose any log I wanted to, but we're going to make it easy. We don't want to choose any fancy logarithms. Choose either ln or log base 10. Natural log or common log. Most people choose common log. So it's called common. Are you okay getting from here to here? We can do whatever we want as long as we do it to both sides. What you can't forget to do is do it to this side too. Because a lot of people, they'll do it to this side because they see that x. They'll forget about this side. It is an equation. You got to do both sides at the same time, exactly the same thing. Do you follow me on that? Now, why does this work for us? Well, I want you to think back to your logarithm properties and look at the left-hand side. There was one property I said, this is the coolest property. Without this property, we can't solve equations. That was like 2 days ago. What property am I talking about here? What can you do with this? If you don't know right now, you should refresh your memory on those properties because you don't know them well enough. What can you do with this? I could write it differently. What can you do with that? Specifically, I'm looking at the exponent. What can you do with the exponent? Yeah. Yeah. Do you remember the power property? I said, I got so excited. I said, this is cool. This is awesome. And you're like, I don't care. Just moves a number. Here's why it's so cool. If you remember anything about the power property, I said, whenever I have an exponent, which I have right here, I can move that to the front of my logarithm. Do you remember that property? So instead of having 3 to the x, I have x times log 3 equals log 7. You okay with that one? Now, why does it make it cool? Hey, check it out. You've got x times something. That's a number. Log 3 is a number you can plug in your calculator, right? That's a number. How do you get rid of x times some number? How would you get rid of that log 3? As long as we divide by both sides. Or divide both sides by that. Not just the left-hand side, but also the right-hand side. What's going to happen on the left-hand side of our equation, folks? How much do we get?
X.
On the right-hand side, I hope you're seeing why all this stuff is coming together for you. This is why I was so particular on those properties. Said you can do some things, but you can't do other things. This is one of those things you can't mess with. It doesn't look like any of those properties, so you just leave it alone. And you're done. That's it. Have you solved for x? Is x all by itself and have some expression without x on the other side? That's your answer right there. Is it a number? Yeah. Could you figure it out? You could approximate it. Put it in your calculator. You can put log 7, log 3, divide those two numbers, and get some approximation for that. Raise your hand, feel all right with this so far? Good, all right. So, the first thing you do, I'll write a couple notes. Number 1, you look for common bases like this. Why? Because your answers are nicer over here if you don't have a logarithm. You with me? You can work with that easier. So, number 1, you try to find common bases. If you can't, then you take a logarithm of both sides. Let's do like one more example together. I'll model for you the thought process on dealing with exponentials. That way you can kind of see how I'm thinking about it, maybe think about it the same way. So the first thing you're looking at, number 1, you identify what type of problem you have. In this case, I'm looking at that and I say, is this an exponential? Is it? Definitely an exponential. The x is in the exponent spot. That makes it exponential. Second thing I do is I try option number 1. I say, can I find common bases between 2 and 5 in any way whatsoever? If I can't do that, then option 1's off the table. I go down to option 2. If option 1's available, it's easier, it's nicer because you get whole numbers. Or you get fractions, or you get something without logarithms. But if option 1's off the table, option 2 comes along and says, you need to take a log of both sides. So I'm looking at that, I go, yep, exponential, no common bases. That means my next step is to take a log, not just of the left-hand side, but also of the right-hand side. After that, we only use one property. The one property we use is the power property for logarithms. It says any exponent can be moved to the front of our logarithm. And from there, it's kind of an easy problem to solve. We just have to divide both sides by whatever's being multiplied by our x. And sure, it looks a little nasty, but that's our answer. Log of 5 over log of 2. They're pretty quick, right? Is the math really, really hard? Just remember that the last like 3-4 chapters haven't been super hard math. It's just, well, maybe the quadratic formula. But besides that, I mean, it's just remembering what you can and what you can't do, remember the properties and knowing how to apply them. I guess that makes it hard if you're really not good at remembering that stuff. But that's really all we need to do in here is really focus on what you can and can't do with logarithms and how to solve these exponentials. Once you try one on your own, I'll change the problem just slightly and then we'll move on. Okay, so we think about it. Is it an exponential, first off?
Yes.
For sure. Can you find common bases?
No.
No, if you could, then you'd be doing it a different way. You just write them with common basis, set your exponents equal to each other, and solve that. You'd get a nice value. However, if you can't find common bases, well, we know there's another option. There is, you can take a log of both sides. What do you do now? Okay, very good. We got to move that x. Otherwise, we're not going to be able to do anything with this, right? Because it's in the exponent spot. The reason why we have to take a log is because that log property says, oh, you can move the x out front. That's what moves it from an exponent to something we can work with. That's why we use those logs. Show of hands, how many people made it that far, the first 2 steps? Good deal. Last step, what are you going to do? By what? Log of 9 over log of 5. What's our base again, by the way?
10.
So we're talking about base 10 logs. You can choose any logarithm you want. People usually choose a base 10, a common log for that. Now, one question, can I change the problem just a little bit? Would you still be able to do it? So up here on the top, let's not just have 5 to the x. Let's have 5 to the x minus 1. Let's go through the process again. Could you find common bases here? No, you can't. You can't do anything with that. So you'd still be taking a logarithm of both sides. So that step's still the same exact thing. However, when you look at your exponent, can you see what you're moving to the front of your logarithm now? Is it simply the x?
No.
What are you going to move?
X minus 1.
Okay, so you move the whole thing. That whole entire exponent has to move to the front, no matter what it is. It could look nasty, right? But as long as you know that that's an exponent and you have a logarithm now, whatever this expression is, that whole thing moves to the front of your logarithm, whatever it is. So we're going to get an x minus 1, log of 5 equals log of 9. Now I've made one pretty major mistake here. What's the mistake that I've made? I've omitted something that I need. Yeah, you absolutely have to have the parentheses because you're multiplying that entire exponent. So that's kind of important. Not kind of. That's really important. You all right with this one so far? Now, what are you going to do?
Divide by x.
Not divide by x minus 1, because that would put an x underneath that. That's going to be real bad. We want to get the x by itself. Now, you have options. One of them is not a good option. One option is distribute. You don't want to distribute. You don't want to distribute. What you want to do is still get rid of the log of 5. How do you get rid of that log of 5 if it's being multiplied?
Divide both sides.
Just divide it. It's the same exact steps. Same exact thing. So notice if I divide by log of 5, it's still going to be simplified out of that expression. You still all right with that? So now what am I going to get on the left-hand side? Equals log of 9 over log of 5. Am I done?
No.
There's only one more thing I have to do. What's that one more thing?
Add 1.
Add 1 to both sides. The 1 is just going to be tacked on to the very end of your expression, okay? So you're going to add 1 here. We'll get x equals log of 9 over log of 5, and then plus 1. There's no way to make it look nicer. All right, you could use the change of base in reverse and get log base 5 of 9, but that wouldn't help you because you couldn't plug it in a calculator to approximate it. That's about as good as we can make it. That's it. Would you rate have you feel okay with these 3 examples? Good, all right. Guess what? That's as far as we go on solving exponentials, because now you know how to do every single exponential. If you can find, there's only 2 cases. Either you find common bases, you know how to do that, or you can't. Now you know how to do that. The next thing we've got to do is look at how to solve some logarithmic equations. Now, what do you suppose is going to happen here? If we need logarithms to solve exponentials, what do we need to solve logarithms? We need exponentials. Right? We need one to solve the other. Notice how we had to have logarithms here. We had to have them. If we didn't have logarithms, you couldn't solve that, because logarithms are the inverse to an exponential. Exponentials are the inverse to logarithms. You've got to have that in order to solve it. If you just look at that, you're not going to really, unless you spend a lot of time thinking about it in your head, you're probably not going to be able to solve that very easily. However, if we use the fact that we can write this as an exponential, if you're good at that, this becomes a pretty easy problem. So let's check it out. So the first thing we're going to do with our logarithms, right off the bat, if you see a logarithmic equation, you are going to write it as an exponential. So let's try it. Why don't we write that as an exponential? Can you tell me, ladies and gentlemen, what is your base here?
4.
Good. What is your exponent? What do you think?
2.
So we should know that this can be written 4 to the second power equals how much?
X minus 2.
Yeah, remember those parentheses are important, right? Saying what's inside of our logarithm. X minus 2. You okay getting that far? We practice that a lot, right? A lot. Let's just solve it. Let's go. What's 4 squared?
16.
So we're just going to write 16. Can you solve that for x?
Yes.
Add 2 and you're done. Hey, we just solved the logarithm. Is it really, really hard? No, not really. You just have to remember that you need exponentials for it and be able to write the exponential appropriately. After that, it pretty much falls into place. I mean, we can square numbers, we can add, subtract, we can solve basic equations. You just need to remember that we have to absolutely have either common bases or logarithms for exponentials, and you have to have exponentials for logarithms. Let's go ahead and do one on your own here. Okay, let's look back at this. Of course, we have a logarithm. There's not much we can do unless we know what an exponential is. We've got to write it as an exponential, so you should have done 2 to the 5th equals x minus 1. Did you make it that far?
Yes.
Good deal. How much is 2 to the 5th?
32.
Okay, don't make the quick mistake of giving me 10. All right, don't just multiply those in your head. It's easy to do on a test. You're just going really fast, you go, oh yeah, 10. Don't do that. I mean, that'd be a real good way to screw up an easy problem, okay? So we're going to go ahead and write 32 here equals x minus 1. We'll add the 1. X equals 33. Yes, no?
Yes.
Well, now this problem's a little bit different. This problem has 2 logarithms on one side of the equation and then a number on the other side. It looks a little bit different than these ones. These were 1 logarithm already, yeah? So is there something we could do, though, to this side of our equation to make it 1 logarithm? You see, you can't do this process unless you have exactly 1 logarithm equal to a number. That's what you have to have. So right here, this is messing us up. Notice how I have those 2 logarithms, right? You'd be like, okay, yeah, well 6 to the 1st power equals, but you'd have nothing to equal because you have those 2 different logarithms there, 2 logarithms. Can you put them together?
Yes.
That's why we study those properties. How do you put together a log plus a log with the same base?
Multiply.
Good. So I could do log base 6 still. Is it x plus this or times this?
Times.
Right? Now you have 1 logarithm. What's your base?
6.
Okay, now I'll let you do something right here if you want. You can distribute now, just rewrite it with distribute, or you can distribute later. It really doesn't matter where you do the distribution. Ultimately, you're going to be distributing. So, I'm sorry, what was your base again?
6.
6 to what power?
First power.
The first, so 6 to the 1st power equals what?
X squared plus
X.
Sure, that whole entire expression, right? So we're going to get, I'm going to write it like that just for now, just so you see where it's exactly coming from. We've got 6 to the 1st equals inside, just like 2 to the 5 equaled that expression right there. Ladies and gentlemen, are you okay with that so far? So same idea. How much is 6 to the 1st?
6.
On the right-hand side, sure I can distribute. That's x squared plus x. Oh my gosh, do you see it? Do you see it? What do you have? You got, what's up there that should tell you exactly what to do here? X squared, our nemesis from even before this class began. Didn't I tell you if you didn't know how to factor, you ain't going to pass this class? Woo! It's everywhere. It's everywhere. That x squared should say something to you. It should tell you exactly what to do right now. What are you supposed to do right now?
Subtract the 6.
I got to get 0 on one side because we're going to be factoring or using the quadratic formula. So if I subtract 6, I get 0 equals x squared plus x minus 6. Why are we doing that? Because we need to know how to factor that or use quadratic formula. And the way to do both is to have 0 on one side. So after you get your x squared, we need to know, hey, don't get stuck here. Man, you know all this. You know this stuff, right? This is old stuff. This is the new stuff. If you can make it down to here, finish it off strong. You're going to try to factor first. If you can't factor in 10 seconds, then use quadratic formula. Can you factor that one?
Yes.
So this is 0 equals probably something like plus 3 minus 2, yeah? Are you done?
No.
No. What do you do now? Good. So we know x equals negative 3 and x equals 2. We're starting to really wrap everything together in these chapters now, in these sections. Just using a lot of old stuff. So we have logarithm properties combining logs. We've got exponential property, making sure we know how to write that as exponential. That's not too bad. That's exactly what we did over here. After that, you can ignore this. This is just a simple equation. 6 to the 1st is 1. Distribute. That's x squared. X squared, say get everything to one side and 0 on the other side. Make sure your x squared is positive. Make sure your x squared is positive. That way you can factor pretty easily in most cases. Set each one equal to 0. We get by the 0 product property. Solve each one down. We get negative 3 and we get 2. So far so good? Now, this is an important piece for you. Plug these numbers in. If you plug in 2, you get 2 and you get 3. Yes? If you plug in negative 3, you get negative 3 and you get negative 2. There's one thing about logarithms that you need to know. the inside of a logarithm can never be negative. The inside of a logarithm. So which one of these things does not work? Negative 3 does not work. Okay, 2 is okay, negative 3 does not work. Not simply because it's a negative, but after I plug it in, the inside of my logarithm is still negative. Does that make sense? So don't just arbitrarily cross out any negative numbers that you have. I'm saying that explicitly. Don't just cross out any negatives that you have. You have to think about it and plug it in. Because if I had like 4 minus x and 5 plus x, neither of those would be negative. They would both be positive. They would both be solutions. Are you with me on that? So don't just cross them out because they're negative. Cross them out because when you plug it in, the inside of the logarithm is negative. There's a difference there. So that's a solution, but that one's not. Logs cannot be negative. So our ideas here are we're going to write these as one logarithm first and then as an exponential. Second note, the inside of a log cannot be negative. That might eliminate some solutions for you. Okay, I'd like you to try one on your own up here. It's really similar, just make sure you can handle it. Go ahead and solve that. Similar problem. Bless you. Hey, what's the first thing you're supposed to do on these equations here?
Rewrite it.
Rewrite it. Okay, good, because unless we have one log, we're really kind of stuck. So hopefully you did that first. If you haven't, go ahead and rewrite that as one log first. When you have the addition between logs, we're multiplying the inside of those logarithms. So your very first step should be log base 5 still, x times x plus 4 equals 1. Did you make it that far? Okay. What's the next step that you're supposed to do?
Write it as exponential.
At this point, we have one logarithm. It'd be pretty easy to write it as an exponential. So that's what we should do. Either distribute right now. You can do that. You can get x squared plus 4x. Make sure we know how to distribute correctly. You can do that now and then write it as exponential, or write it as exponential and then distribute. It really doesn't matter at this point. So I'll do the exponential first. I like doing that. Five to the first power gives you exponential. A lot of times you're going to see a 1 right there with these because you're raising the number to that power. And if I have something like a 3 or a 4 over there, that's going to be like 125 or 625. That's going to be up there really, really, really quick, right? And it's going to be very hard to factor. So typically you'll see a 0 or a 1. Just a side note, if it is 5 to the 0 power, if that was a 0, how much is 5 to the 0?
1.
It's 1, it's not 0. It is 1, okay? So be careful on that. If you have something to the 0 power, you're going to get 1 out of it. Can you make it this far, folks?
Yes.
Okay, at this point we do a little bit of work. We've got 5 equals x squared plus 4x. And that should key into doing something. What are you going to do at this step right now? Yeah. That's exactly right. I'm going to move up there. And now it's time to factor. Good old factoring. If you can't factor, quadratic formula will still work. But on most of these you'll be able to factor, otherwise it may become really long problems. Possible, but really long problems. Hopefully you got +5 and -1. That means we're going to set each of them to 0. We'll get x equals -5, x equals +1. And it appears that we have two solutions. However, when we plug them in, the 1's just fine. We get 1, we get 5. That's great. They're both positive inside our logarithms. However, the -5 is not. Because you're going to get -5, you're going to get -1. That's not okay to have a negative inside a logarithm, so we're going to cross this one out. Wish if you got down to -5 and 1 and then crossed out the -5. Good deal, all right. Hey, now our next example over there, we still have those two logarithms. Is there a way we can combine those logarithms? Yeah, we can. Not the same way as this, right? Over here, this plus meant multiply or product. What does that minus mean? What's a log minus a log mean? How do I put those together? Yeah, we're going to divide. Oh, by the way, what did I forget up here? Did I forget something?
No, it's just left-handed or something.
Ah. So I didn't forget the base. You need to know that if I have log there, what's the base?
10.
So yeah, I can combine these. I'm going to get a common log. What's going to be on the top of my logarithm?
X minus 1.
Notice how it's really important to understand that two logs are becoming one log. If you had put a log over a log, you'd be stuck. You'd have nothing to do right then. That would be a bad thing. Right now, we can combine these two logarithms as log of this first one divided by the second one equals 1. So far, so good? Now, it looks a little weird, but can you write that as an exponential right now? As soon as you get one logarithm, you're supposed to write it as exponential. What's our base again?
10.
So I'm going to have 10 to what power?
First power.
Equals.
X minus 1 over x.
Now it looks kind of nasty, but just stick with it. Okay, don't give up yet. Actually, don't try not to give up ever. I see somebody just skip problem. Like, oh, you're killing me. Just one step and it'd be easy. How much is 10 to the first?
10.
I know you're all afraid, well, not all of you, but some of you have nightmares about fractions. I know this for a fact. Because some of you told me, I have nightmares about fractions. But think about what the fraction means. What we need to do is undo this fraction, and now it has an x on the bottom. How do you get rid of the x on the denominator of fraction? You what now? You multiply by x, because you have something being divided by x, right? So check it out. Use your LCD idea. LCD is simply x. Multiply both sides by that x. What's going to happen on the right-hand side, folks? You're going to eliminate those. What's going to be left when you simplify out that x? What's it going to be? Sure. Over here, how much are you going to get? It's a little too close. Can you solve it?
Yes.
Yeah. Yeah, you can solve that. It's 10x equals x minus 1. You get rid of the smaller variable. Which x are you going to remove?
The x.
That one. Subtract x. And now,
Divided by 9. Is it going to end up being negative though?
well, we're going to look at that. So, can you still do the problem? Still same idea. Combine your logarithms with some sort of log property. They're either going to be added or subtracted. Adding means product, subtraction means a division. Set up an exponential, we all know how to do that now. You take your base to your exponent equals whatever's inside your logarithm, and then work it out somehow. You might have to distribute and factor. You might have to multiply both sides by a value and then solve it with a simple problem here. Are you okay on getting that -1/9? Now, someone's already identified the problem, but there's a problem here. If you plug that in, you're going to get -1/9, and you're going to get -1/9. Is that okay to have a negative inside of a logarithm?
Yeah.
No, so there's no solution here. All that work for nothing. Well,
I know you do.
it was worth a shot.
If you would have been lazy and just put no solution this time, you'd be right.
If you were lazy and you would have done that, yeah. Would I give you credit for it? No. But
You're looking at us.
you'd get like 1 point for being a smart man. Okay. Why don't you give that one a try? Put it together with some sort of log property. Write an exponential, then solve it. It is similar to the last one, but make sure you can do it on your own. Do you put these logs together with addition, subtraction, multiplication, or division? So we should have one logarithm over one logarithm, or a logarithm of something over something. Which one? The second. Good. The second one. Not a log over a log, right? A log of a fraction. So you should have a log x plus 3 over x equals 1. Did you make it that far? Okay. Now it's time for your exponential. You need to identify the base. What's the base?
10.
So we have 10 to the first power equals x plus 3 over x. Still okay. Did you all make it that far?
Yes.
All right. 10 to the first, that's kind of nice. Again, you're usually going to get small numbers over here because those are exponents. You have them raised to stuff like a 4, that's a big number already. Okay, that's like 10,000. That's too big to work with, and well, it's not too big to work with, be okay. But you're going to get very awkward answers. So 10 equals x plus 3 over x. Of course, how are we going to get rid of that x? Yeah, don't get stuck here. Understand that in order to remove an x off of the bottom of a fraction or denominator, you simply have to multiply by it. Acts like an LCD, that is the LCD. We get 10x equals x plus 3. And lastly, we'll get rid of our smaller variable, subtract that x. And finally, tell me something. This time, is it a valid solution or not? What do you think?
Yes.
Why?
Because you're all going to get positive answers.
Not because this is positive.
Plug it in, you're going to get positive.
Because when you plug it in, the inside of the log is still positive. Does that make sense? Okay, if I had like 1 minus x, that wouldn't be a solution. Because you'd have 1 minus 1/3, that would be negative. I'm sorry, if I would have had x minus 1, that wouldn't have been a solution. 1/3 minus 1 would be a negative 2/3. That wouldn't be appropriate. So it's not just that that's positive, it's that when you plug it in, the inside of the log is still positive. Do you see the difference there? I hope you're seeing the difference there. Oh, one more thing I want to show you. Check this out. If I initially gave it to you as this problem, if I give you that, can you guys see that the first thing that we would need to do is get both the logs on one side of the equation? That way you could, are we ready? The first thing you need to do is get both logs on one side of the equation. That way you could combine them in some way. So notice that this problem is this problem. Do you guys see that it's that problem?
Yeah.
The first thing you would do is subtract log x. The idea is you have to get them on the same side of the equation, that way you can combine it. After that, it is that problem. Then you work it all the way down. So if you ever have something with logs on different sides, get all the logs to one side, combine them with your properties, and then you can write an exponential. How many people see that one all right? All right. Hey, let's work with something else. Let's work with that one. Are these still logarithms?
Yes.
Do they have an L in front of it?
Yes.
Are they still logarithms?
Yes.
What's the base here?
E.
Oh yeah, it's not 10, it's not 2, it's E. Base is E. That's what the natural log meant. Hopefully you worked with those on some of your homework. So let's go ahead and stick with the same properties. What are you going to do first if you have a log plus a log? Those are still logs. The properties still work for those. What are you going to try to do first with that? What do you think? You're going to leave them as two logarithms? Did we leave this as two logarithms? Can you combine those? Are you going to combine them by addition, subtraction, multiplication, or division? What do you think? So in our case up here we have natural log of 5 plus natural log of x. That means we can combine them to one natural log of, is it 5 plus x or 5 times x?
5 times x.
5 times x equals 0. You sure you're okay with that? Works just like any other logarithm. It just has an n there instead of a log there. Works exactly the same. Again, what is your base here? Because right now we have one logarithm. The next step is to write this as an exponential. What is your base here, folks? E. What's your power?
0.
Good. Equals how much?
5x.
Hey, now here's a good one. How much is e to the 0? Is it 1 or is it 0?
1.
It's 1. So don't let your mind trick you and go, oh, it's 0, because there's a 0 there. We're not multiplying, we're taking a power. E to the 0, anything to the 0 power is 1. Can you solve it?
Yes.
Yeah, what are you going to do? Hey, you're done. You're done. One more thing I want to show you with this problem. What if this is not a 0? What if this is like a 2? If that's a 2, would you still do the same thing here? Okay, and then you'd have a 2 here. What would this become?
E squared. Then you have to use the square root.
You'd have a square there, yes? Okay. Could you still divide by 5? Because right now you have e squared, you're going to leave the e squared. That's the e's a number, this is appropriate, it's fine. Leave the e squared, just divide by 5. We get e squared over 5 equals x, and that's your answer. Are you okay with that one? Exactly the same, only now you don't have a 1, you have e squared. We've actually seen stuff like that before in this class when we were dealing with logarithms the very first time. Okay, would you raise your hand feel okay with solving exponentials and solving logarithms? Awesome. You want to see an application? Oh, come on, it's the last one. An application is something you have on your iPhone.
Games.
Hey, games! I have calculators.
That's all bad.
I have 4 graphing calculators on my iPhone.
Oh my gosh.
They're all cool.
I have a thesaurus.
I don't care about words.
Oh, the irony.
Read the problem. Read the problem. Immediately, you need to be able to determine which of these two formulas you're going to use. I've given you 2 formulas in this class for interest. We're talking about interest and investment right now. One is dealing with compounded continuously, one's dealing with compounded any other way. Can you tell me which is dealing with continuous compound, the left one or the right one?
Right one.
Good. You should have dealt with that on your homework, right? This would be compounded any other way. So which one are we going to use, the right one or the left one?
Left.
If I had said compounded continuously, you'd be using this one. If I say anything else, you're using that one. So we're going to eliminate this right now. Let's go ahead, let's try to identify all these letters. Firstly, A is the amount that you're going to have after your investment's over. P is your principal, R is your rate, N is your number of compounds, T is your number of years. How much is your, well, let's start here. How much is your P? What are you starting with? So I know that this is going to equal 1,000. Okay, the 1 doesn't change. But what's your rate here, ladies and gentlemen?
0.06.
Okay, 6% good, 0.06 over somebody else on the right-hand side. How many compounds do we get out of this particular example? Why? Where are you getting the 4? Quarterly means 4. Good. 4 goes here. 4 also goes here. These numbers are tied together. They're the same number. Wait, hey. How about T? How much T do we get? How much years is this?
X.
Do you know? Does it say? In fact, how long means find T. We're asking the time. We're asking how long is it going to take to double an investment. Folks, are you okay on plugging in these numbers right here and understanding that this is what we're actually looking for? Are you sure? Well, here's the problem though. Can you think about, don't say it right away, I want everyone to think about this. Can you think about what number goes here? Just think for a second. If I'm asking you to double an investment, what was your investment?
1,000.
What's double that?
2,000.
So I'm asking you, how long is it going to take to get 2,000 bucks? Double investment is twice that. So if you invest $1,000, you're looking, when are you going to get 2,000? Isn't that something that might be useful? Say, how long do I have to keep this money in there to double my profit, or to triple it, or to increase it by 50% or so? That's kind of a useful thing to know. So we are actually trying to solve for T. Here's how we're going to do it. It takes just a couple minutes. Just follow me through one time. I'll give you one little piece of advice on this to look at it kind of a slightly different way, and then we'll be done. Firstly, you're going to work to try to get to that T. The first thing you've got to do, don't distribute, you can't distribute that. That's got an exponent to it. The only thing you need to do is get rid of that 1,000. You do that by division. How much is 2,000 divided by 1,000, folks?
2.
So 2 equals 1 plus 0.06 over 4 to the 4t power. Now, this is going to look weird, but I need you to identify that this right here is actually an exponential. Do you see it? That has a base of 2. This has a base of, why don't you figure that out for me? Do 0.06 divided by 4 and then add 1. .06 divided by 4 should be 0.015. So this is 1.015. Yes? To the 4t. Hey, look at the board. Look. That's an exponential. Do you have common bases? Do you have common bases? Are these the same number?
No.
Can you find common bases? No. So guess what we do? We take a log of both sides. It's the same type of problem. We're going to take a log of both sides over here. And what you're going to get is log of 2 equals log of 1.015 to the 4t. You okay with the logarithm?
Yeah.
It looks funny because you have a decimal, but it's the same idea. Hey, what can you do with the 4t?
Move it to the front.
That's an exponent. So log of 2 equals log, 4t log of 1.015. Raise your hand if you can make it that far, feel all right with that. That's not everybody. Are you guys okay with that? Are you sure? Are you sure? Kind of, sort of. All right. It's the same idea. As soon as you get down to here, plug in numbers, divide by 1,000. That's one number. Raise your exponent. Take a log of both sides. Move your exponent forward. That's what we've been doing for a while now, today. Here's some fancy math. Divide by all the numbers you need to get rid of on both sides. So, for instance, you need to divide by 4 to get rid of the 4. Agreed? You also need to divide by a log 1.015 to get rid of the 1.0 log of 1.015. Do that on both sides. You get t on the left. You get log of 2 over 4 log of 1.015. I'll do the math for you right now. If you do log of 2, that gives you approximately 0.3010. If you do log of 1.015, it's going to give you 0.006466. Now, unfortunately, you shouldn't really round those numbers because you're going to be way off on your number of years if you do, because you're dealing with really small numbers here. So in order to do this the right way, I'm going to do log of 2, and I'm going to press enter. Then I'm going to divide by 4, and I'm going to press enter. That's this part right here. Whatever number you get, you divide again by log, divide again. Remember, this is divide and divide. Divide again by log of 1.015, and what I got out of that is 11.64. $11.64 what? What were we looking for? That's the years. It's going to take you over 11 and a half years to double an investment. Now here is my important question for the day. If I raise my investment to $1 million, will this happen sooner or later?
Sooner. No.
If I raise it to $1 million, if I raise it to $1 million, that's $1 million. If I double my investment, it would be $2 million. $2 million. What would happen? You divide by a million, right? What's a million? What's 2 million divided by 1 million? Hey, it's the same thing. To double any investment is going to be the same amount of time, provided your compounds and your interest rates stay the same. The way you change the amount of time it takes to double investment, interest rate. Mostly it's interest rate. Compounds a little bit. Mostly interest rate. That would tell you the time it takes to double it.